Deep beneath the border of France and Switzerland, protons are smashing together at almost the speed of light, and every time they do, they shatter into pieces our best theory says should not exist. You think the rules of the universe are settled, written down, final. But inside a ring 17 miles around, those rules are starting to crack. We are going to the coldest place in the galaxy, colder than deep space. We will drop antimatter and watch which way it falls. We will find a particle that decays the wrong way, one time in 16,000. If this fascinates you as much as it fascinates me, tap like and subscribe, and come with us. The machine is CERN, and tonight it is bending reality. Prepare yourselves, we begin. Picture a tunnel buried 300 feet under farmland, running in a giant circle beneath two countries at once. That tunnel is the beating heart of CERN, and it is 17 miles around, big enough to swallow a small city. Down there, in the cold and the dark, the fastest race on Earth never stops. The racers are protons. These are tiny pieces, pulled from the center of hydrogen atoms, the same hydrogen found in a drop of water. Scientists strip them out, herd them into a beam, and push them faster and faster with bursts of electric force. By the time the beam is up to full speed, each proton is moving at almost the speed of light. How close? Only about 7 miles an hour slower than light itself. Nothing you have ever seen moves like this. At that speed, a single proton flies around the 17-mile ring more than 11,000 times every second. Blink, and it has already lapped the tunnel thousands of times. Two beams run at once, side by side, racing in opposite directions like two trains on a looping track that will soon be aimed straight at each other. Here is the part that sounds impossible. Each beam carries as much energy as a fast-moving passenger train. All of that force is squeezed into a thread of particles thinner than a human hair. If that beam ever slipped its cage, it would punch a hole clean through solid metal. So the whole machine is wrapped in layers of protection, watched by computers that can shut it down in a fraction of a heartbeat. People often think this machine was made just to go fast. Speed was only the tool. The real target was something far stranger. A set of rules that scientists have trusted for 50 years. Rules they now suspect are hiding a secret. What comes next is the reason they were willing to dig a tunnel the size of a city to find it. For half a century, every particle scientist has carried the same rulebook in their head. They call it the standard model, and it is the most tested idea in all of science. It lists every basic building block of the universe, every tiny piece that makes up you, this planet, and every star you can see. It has passed test after test, sometimes matching real measurements down to a level like guessing the width of the country and being right to the thickness of a coin. That kind of success should feel like victory. Instead, it keeps scientists awake at night, because the rulebook is clearly missing pages. The standard model cannot explain gravity, the force holding you to your chair right now. It cannot explain dark matter, the invisible weight that outnumbers everything we can see by more than 5 to 1. It cannot explain why the universe is full of stuff at all, when the math says it should be empty. A rulebook this powerful should not have holes this big, yet it does. So, scientists did something bold. They built a machine designed to attack their own rulebook. Every collision inside CERN is a punch thrown at the standard model, a test to see if it finally cracks. If the rulebook is complete, the collisions will always behave exactly as predicted, forever, with no surprises. Boring, in a way. But if even one collision breaks the pattern, that break could be the first glimpse of a deeper universe waiting underneath. Think of it like a scientist who spends years building a perfect clock, then smashes it against the wall on purpose. They are not being careless. They want to see which piece flies out that they never knew was inside. To land those punches, the beams must be aimed with unreal precision. Two hairs of particles, each racing at almost light speed, have to be steered around a 17-mile loop and slammed together in a spot smaller than a grain of sand. Miss by the tiniest amount and nothing happens. Steering something that fast is a nightmare of physics. A proton at full speed wants to fly in a straight line and shoot right out of the tunnel wall. To bend it back into the circle, CERN needs a force stronger than almost anything on the planet. The answer to that problem sits in the coldest place in our entire galaxy, colder than the empty space between the stars. To bend a beam moving at almost the speed of light, CERN uses more than 1,000 giant magnets, and each one is a monster. A single magnet stretches about 50 feet long, longer than a school bus, and weighs as much as a small truck. Line them up around the ring and they form a curving wall of magnetic muscle, all working to grab the racing protons and steer them gently back into the circle. These are no ordinary magnets. The force they make is over 100,000 times stronger than the magnetic pull of the whole Earth. The pull that swings a compass needle north, a field that strong could rip a wrench out of your hand from across a room. Making a force that powerful comes with a brutal problem. Pushing that much electricity through normal wire would melt it instantly, like a toaster coil cranked 1,000,000 times too high. So CERN uses a trick that sounds like magic. When certain metals get cold enough, truly, deeply cold, electricity begins to flow through them with zero resistance. No heat, no loss. The current just runs forever, like a river that never slows down. Scientists call this superconducting. The catch is the cold. To reach that state, the magnets have to be chilled to a temperature almost impossible to imagine. We are talking about 456 degrees below zero on the Fahrenheit scale. That is colder than the dark void of deep space. Right now, one of the coldest places in the known universe is not on some distant frozen moon. It is sitting under the border of France and Switzerland, humming quietly. To reach that cold, CERN pumps the magnets full of liquid helium, the same gas that makes party balloons float, turned into a freezing liquid. Ton after ton of it flows through the machine, holding the whole 17-mile ring at a chill deeper than anywhere in nature. Here is the strange beauty of it. Inside the same machine, two wild extremes live side by side. The magnets are frozen near the bottom limit of cold, and the tiny points where the beams crash together will flash hotter than the center of the sun. The coldest and the hottest separated by inches. Getting everything this cold takes weeks. Cooling the ring is slower than freezing an ocean, and warming it back up to fix a problem can cost months of lost time. So the machine mostly stays frozen, year after year, a sleeping giant kept on the edge of absolute cold. Once the beams are locked in place by this wall of frozen magnets, everything is ready for the main event. Two threads of protons racing in opposite directions, aimed at a single point smaller than a speck of dust. At 4 spots around the ring, the beams are allowed to cross, and in that crossing, something is about to happen that turns pure motion into brand new pieces of reality. At 4 points around the ring, the two beams are steered into each other, and the collision that follows breaks one of the most famous rules you have ever heard. Most people believe you cannot make something out of nothing. Inside CERN, energy becomes matter thousands of times a second. Here is how. When two protons moving at nearly the speed of light smash head-on, they do not simply bounce like two marbles. They carry a huge amount of energy, all packed into that blistering speed. In the crash, that energy has to go somewhere, and nature has a secret exchange rate. Energy can turn into matter, and matter can turn into energy. It is the meaning behind the most famous formula in science, the one that links the two. So in the instant of impact, the raw energy of the crash freezes into new particles that were never there before. Tiny specks of matter spray outward in every direction, born fresh from pure motion. It is a little like two cars crashing so hard that the wreckage weighs more than the cars did, with brand new pieces appearing out of the force of the hit. The faster the protons, the more energy they carry, and the heavier the new particles that can appear. This is the whole reason scientists fight so hard for speed. A slow machine can only make light, common particles, the kind found everywhere. A machine this fast can conjure rare, heavy particles that have not existed naturally since the universe was newborn. To find something exotic, you have to hit hard enough to pay for it in energy. Most of what appears vanishes almost at once. These heavy newborn particles are wildly unstable. They exist for a sliver of time so short that light itself can barely cross the width of an atom before they fall apart. Then they decay, breaking into lighter pieces, which break into lighter pieces again, spraying out a shower of debris. That shower is the whole point. Scientists never see the rare heavy particle directly. It dies too fast. What they catch is the spray of lighter pieces it leaves behind, like reading footprints in mud long after the animal has run off. From those footprints, they work backward to figure out what was born in the crash. Now think about the scale of this. At each crossing point, bunches of protons pass through each other about 40 million times a second. In every pass, a fresh burst of collisions blooms and dies. 40 million chances a second to make something the universe has not seen in billions of years. Somewhere in that endless storm of tiny explosions might sit the answer to the questions the rulebook cannot handle. But there is a problem no one can ignore. If these particles die in less time than it takes light to cross an atom, how could anyone ever hope to catch them? The answer is a set of machines so massive they had to carve out caverns to hold them. Cameras built to freeze the fastest events in all of nature. In the summer of 2012, a room full of scientists sat in silence, staring at a screen, waiting to see if a 50-year-old prediction was about to come true. When the answer flashed up, grown adults broke down in tears. One old man in the front row, quiet and grey-haired, wiped his eyes. His name was Peter Higgs, and the particle on the screen was the one he had dreamed up almost half a century before. To understand why anyone would cry over a particle, go back to a giant puzzle in the rulebook. Scientists had a theory that explained why some particles are heavy and some are feather-light. That theory only worked if one special piece existed, a single missing particle that tied the whole idea together. Find it, and the rulebook stood strong. Fail to find it, and the entire picture might collapse. The trouble was, this particle was a ghost. It was heavy, rare, and it fell apart almost the instant it was born. To make one, you needed collisions of unreal power. That is a huge part of why CERN was built in the first place. The machine was, in many ways, a trap laid for a single particle that had been hiding for 48 years since it was first predicted. The hunt was brutal. Scientists had to sift through trillions of collisions, looking for a faint pattern in the debris that only this particle would leave behind. Most crashes made ordinary junk. Only a rare few might carry the fingerprint they wanted. Searching for it was like listening for one specific whisper inside a stadium of screaming fans, then proving that whisper was really there. Two separate teams worked on two separate detectors, on purpose. They did not share their results while they searched. That way, if both teams found the same bump in the data on their own, no one could say it was a mistake or wishful thinking. Two blindfolded witnesses, pointing at the exact same spot, and they did. On the 4th of July, 2012, both teams announced they had found a new particle, right in the mass range the theory demanded. The rulebook had survived its biggest test. The missing piece was real. The newspapers gave it a dramatic nickname, calling it the God particle, a name most scientists actually dislike. They just call it the Higgs, after the man in the front row. The next year, he was given the Nobel Prize, the highest honor in science, for an idea he had first written down as a young man. Here is the number that shows how patient science can be. Peter Higgs waited 48 years between predicting the particle and seeing it appear on that screen. A prediction older than the moon landing, finally caught in a machine that did not even exist when he made it. But finding the particle was only the beginning, because the Higgs is tied to something far larger and stranger, an invisible thing that fills every inch of space around you, right now, and decides how heavy everything in the universe is allowed to be. Right now, as you listen, you are moving through something you cannot see, touch, or feel. It fills this room, It fills the space between the stars. Scientists call it the Higgs field, and without it, you would not have a body at all. You would be a blur of light, racing away at the speed of light, unable to slow down. Start with a strange question. Why does anything have weight? Why is a bowling ball heavy and a beam of light weightless? The old rulebook did not have a clean answer until scientists imagined an invisible field soaked into all of space, like water soaked into a sponge that fills the entire universe. Here is the idea. In plain terms, every particle that makes up you is constantly moving through this invisible field. Some particles push through it easily and barely feel it. Others get gripped and slowed by it. The more a particle drags against the field, the harder it is to push around. And that resistance to being pushed is exactly what we call mass. Mass is really just a measure of how stubborn something is to move. Picture a wide field covered in deep snow. Now send different people running across it. A tiny child in snowshoes skims right over the top, quick and light. A grown adult in heavy boots sinks in with every step, slow and labored. Same snow, different drag. In this picture, the snow is the Higgs field, and how deep you sink is your mass. Light particles wear the snowshoes. Heavy particles wade through up to their knees. This explains one of the most beautiful facts in physics. Light itself has no mass, so it never slows down. The particles of light ignore the field completely, like ghosts walking straight over the snow without leaving a print. That is why light always travels at the fastest speed there is. It carries nothing to hold it back. You might wonder how anyone could ever prove that an invisible field is truly there. This is where the Higgs particle comes in. When scientists smashed protons hard enough at CERN, they gave the field a sharp kick, and the field kicked back by spitting out a single ripple. That ripple was the Higgs particle they caught in 2012. Finding the ripple proved the field was real. You cannot see the ocean in the dark, but a splash tells you the water is there. Let this sink in for one moment, in the real sense. The weight of your own body, the reason your feet press against the floor, traces back to how strongly your smallest pieces drag through an invisible field that has been there since the universe was seconds old. Take the field away, and you would weigh nothing, and neither would the sun, the planets, or the atoms in your hand. The rulebook had passed its greatest test. The field was real, the particle was found, and for a while it looked like physics had won. Yet the deeper scientists looked, the more they realized the ordinary matter around us, all of it, might be only half the story, because the universe also allows a mirror version of every particle, a twin with the opposite charge. And to study that twin, CERN needed to become the strangest factory ever built, one that makes the rarest substance in existence. To catch a particle that lives for less time than it takes light to cross a single atom, scientists needed cameras unlike anything ever built. So they carved out underground caverns, the size of cathedrals, and filled them with machines that weigh more than the Eiffel Tower. These machines are called detectors, and they wrap all the way around the points where the beams collide. Imagine a giant onion, layer inside layer inside layer, with the collision happening right in the very center. Each layer is built to catch a different kind of debris flying out of the crash. As particles burst outward, they punch through the layers one by one, and each layer records where they passed and how fast they moved. The scale is hard to believe. One of these detectors stands about 80 feet tall, as high as a 6-story building, tucked in a cavern deep underground. Its rival weighs around 14,000 tons, heavier than the famous Iron Tower in Paris, packed with so much metal it took years just to assemble. Yet every giant piece is aligned with the care of a fine watch. Now for the truly wild part. These are cameras, and they take pictures. But they do not snap a photo now and then. They capture the aftermath of collisions about 40 million times every single second. 40 million snapshots a second, each one freezing a burst of newborn particles in mid-flight. No normal camera on Earth comes close. To do that, A single detector is stuffed with something like 100 million tiny sensors, all firing at once. Think of the camera in your phone and its handful of megapixels. Now imagine a camera with 100 million sensing points, shooting tens of millions of frames a second, buried under a mountain of steel. That is what it takes to read the footprints of particles that die almost the instant they are born. Different layers do different jobs. The inner layers track the tiny curling paths of charged particles as they bend in the magnetic field, since a particle traveling faster and with more energy bends less. Outer layers act like walls that stop and measure the energy of the debris slamming into them. Put it all together, and scientists can rebuild the whole story of a collision, working out what appeared, how heavy it was, and how it fell apart. Here is why the detector has to be so complete. The rare, exciting particles never reach the sensors. They die in the center far too fast. What reaches the layers is only the spray of lighter pieces they leave behind. Miss even a few of those pieces, and the whole story falls apart, like trying to solve a crime with half the clues erased. So the detector is built to catch nearly everything, in every direction at once. But catching the collisions creates a problem so enormous it almost sinks the whole project. 40 million pictures a second, from 100 million sensors, running day and night. That is a fire hose of information so vast that no computer on Earth, not even all of them combined, could ever hope to store it all, which forces scientists into a ruthless choice, made in a sliver of a second, about which collisions to keep forever and which to throw away and lose for all time. Every second, CERN faces a decision so extreme it sounds insane. Out of 40 million collisions, it must throw almost all of them into the trash forever, keeping only a tiny handful. Choose wrong, and the greatest discovery in history could vanish before anyone ever sees it. The reason is a flood of data beyond anything you can picture. If scientists tried to save every detail from all 40 million collisions each second, they would fill up the world's biggest hard drives in moments. The raw fire hose pouring out of a single detector, if you kept all of it, would pile up faster than a stack of movies reaching past the moon. No storage on the planet could hold that river, not even close. So, the machine has to be brutal. In less than the blink of an eye, special computers glance at each collision and ask a simple question. Does this look ordinary and boring? The kind of crash seen a billion times already? Or does it show a hint of something rare and heavy, worth a closer look? The boring ones, which are almost all of them, are erased instantly and lost forever. Only the most promising few are saved. Think of it like a photographer at the busiest moment in the world, snapping 40 million shots a second, with room to keep only a few hundred. She has to decide, faster than thought, which images might hold something no one has ever seen, and let all the rest disappear. That is the job these trigger computers do, all day, every day. Even after this savage cut, what remains is staggering. In a single year, CERN still stores enough saved data to fill tens of millions of everyday laptops. It is one of the largest piles of information humans have ever gathered in one place, and it grows every time the machine runs. No single computer could ever chew through all that. So, scientists did something clever. They linked together hundreds of thousands of computers in labs and universities all over the planet, tying them into one giant shared brain. When a scientist in one country needs to study the data, the work is quietly spread across machines on many continents at once, all crunching pieces of the same puzzle. The whole world becomes one computer. Here is the humbling truth buried in all of this. The discovery of the Higgs particle, the one that made grown scientists weep, was hidden inside just a few crashes out of trillions. If the trigger computers had made the wrong split-second call and tossed those crashes away, the answer might have slipped through our fingers. Somewhere in the ocean of deleted collisions, who knows what else was thrown out before anyone could look? That thought haunts physicists. Every day, the machine keeps only the collisions that match what scientists already expect might be interesting. But the strangest discovery of all might look boring at first glance, easy to miss, easy to erase. Still, some prizes are worth building an entire second lab to chase, because CERN does more than smash ordinary matter. It builds, atom by atom, the rarest and most valuable substance in the entire universe, a mirror version of everything you are made of. There is a substance so rare that all the amount humans have ever made, gathered together, could not even power a single light bulb for more than a few minutes. It is the most expensive material in the universe, worth more than gold, more than diamonds, more than anything you could name, and CERN is one of the only places on Earth that can make it at all. It is called antimatter, and it is the strangest twin in all of science. For every kind of particle that makes up you, nature allows an opposite version, a mirror copy with the reverse electric charge. The tiny bits with a minus charge have twins with a plus charge, and the plus charged bits have twins that are minus. Same weight, opposite sign, a perfect reflection of ordinary matter. Now for the terrifying part. When a piece of matter touches its antimatter twin, both vanish in a flash. They do not break apart or bounce away. They destroy each other completely, turning their entire mass into a burst of pure energy. Nothing else in nature is this violent or this total. A speck of antimatter meeting a speck of matter releases far more energy, pound for pound, than any bomb ever built. This is why making antimatter is a nightmare. The instant you create it, it wants to touch the ordinary matter all around it, the walls, the air, the tools, and annihilate in a tiny flash. So scientists have to build it and hold it without ever letting it touch a single thing. Imagine trying to make a snowflake that explodes the moment it lands on anything. So you must keep it floating in mid-air, forever, never touching the ground. CERN builds antimatter piece by piece, starting with the mirror twin of the proton. Then, with incredible care, it coaxes those pieces to join with the mirror twin of the tiny particle that orbits inside an atom. Put them together correctly and you get an anti-atom, the reflection of the simplest atom in existence, a mirror version of the very hydrogen found in every drop of water. The amounts are almost laughably small. After years of effort, the total antimatter ever made by humans would fit on the head of a pin with room to spare, and most of it lasts only a flicker. If you wanted to buy a single gram of it, and you could not, the price would run into the trillions of dollars, because making that much at today's speed would take longer than the age of the universe. So why chase something this hard to make and this eager to destroy itself? Because antimatter guards a secret about why we exist at all. If matter and antimatter are perfect mirror twins, they should behave in perfectly mirrored ways. Scientists want to test that, atom by atom, to see if the mirror is truly perfect, or if there is a tiny flaw in the reflection. To run that test, they first face an impossible-sounding task. They have to catch a handful of these anti-atoms and hold them still, in one place, without ever letting them brush against a single wall of the trap. And the tool they invented to do it is a cage made of nothing but pure magnetic force. Holding antimatter is like trying to cup a flame in your bare hands without getting burned, except 1,000 times worse, because the moment this flame touches anything at all, it detonates. Scientists needed a cage that could grip an antiatom while touching it with nothing solid whatsoever, so they built a bottle made of pure force. Here is the challenge that makes it so hard. An antiatom, like a normal atom, has no overall electric charge. It is neutral. That matters because the easy way to trap charged particles is to push and pull them with electric force, the same way a balloon rubbed on your hair sticks to a wall. But a neutral anti-atom shrugs off that trick. Electric fields cannot get a grip on it. It would drift straight into the wall and vanish in a flash. So scientists reached for a subtler handle. Even though an anti-atom carries no overall charge, it behaves like an unbelievably tiny magnet, with a faint magnetic pull of its own. That whisper of magnetism is the only handle nature gives you, and it is barely there, thousands of times weaker than the grip you would have on a charged particle. Trying to hold something by that thread is like lifting a car with a single strand of spider silk. To make it work, they surround the trap with powerful magnets shaped to form an invisible valley in the middle. An anti-atom placed in that valley feels a gentle nudge back toward the center whenever it tries to drift toward a wall. Picture a marble rolling around inside a smooth bowl. Let it go, and it always rolls back down toward the bottom, never quite escaping over the rim. The bowl here is made entirely of magnetic force, holding the anti-atom in the empty center where it can touch nothing. Even that is not enough on its own. A warm anti-atom zips around too fast and flies right over the rim of the magnetic bowl, straight into the wall. So scientists must first chill the anti-atoms to a temperature just a hair above the coldest anything can ever get, near the bottom limit of cold itself. Only when the anti-atoms are slowed to a crawl by that deep freeze do they move gently enough to stay trapped in the valley. For years, scientists could hold their anti-atoms for only a flicker before losing them, but the tricks got better. Colder traps, stronger fields, steadier magnets. Slowly, the record climbed, from a fraction of a second to seconds to minutes. Eventually, one team managed to cradle these anti-atoms for more than 16 minutes at a stretch, an eternity for a substance that destroys itself the instant it touches the world. 16 minutes may not sound like much, but it is long enough to do something no human had ever done before. Long enough to hold a piece of mirror matter still, study it, and even shine light on it to read its secrets. And it is long enough to try the boldest experiment of all, to take a handful of these trapped anti-atoms, release them, and watch, very carefully, which way they fall. Because a strange and beautiful question had been waiting for centuries. When you drop antimatter, does it fall down like everything else? Or does it fall up? More than 400 years ago, a man named Galileo is said to have climbed a leaning tower and dropped different objects to see how they fell. Now imagine repeating that ancient test, except instead of dropping a rock, you drop the rarest substance in the universe. And nobody, not even the greatest scientists alive, is fully sure which way it will go. Everything you have ever seen falls down. Drop a ball, a phone, a feather, and gravity pulls it toward the ground. This is the most familiar force in your life, but every object you have ever dropped was made of ordinary matter. Antimatter had never been dropped and watched, not once in all of history. So a wild question hung in the air. What if antimatter falls up? It sounds crazy, and most scientists doubted it. Yet a small chance remained that gravity might treat the mirror twin differently, pushing it away instead of pulling it in. If that were true, it would shatter one of the deepest ideas in all of science. The rule that gravity treats every kind of stuff exactly the same. A single anti-atom drifting upward would rewrite the laws that describe falling apples, orbiting planets, and the shape of the entire universe. The stakes could not be higher. Testing it was brutally hard. Remember, an anti-atom vanishes the instant it touches anything. So scientists built a tall trap, standing upright like a chimney, and filled the center with anti-atoms held in a magnetic grip. Then they slowly weakened the trap at the top and the bottom at the same time, opening the door on both ends, and watched to see which way the anti-atoms escaped. The logic was simple and beautiful. If gravity pulls antimatter down, more anti-atoms should slip out the bottom of the trap than out the top. If gravity pushes it up, more should escape from the top. Count where they annihilate, and gravity itself gives you the answer, written in tiny flashes. The catch was that the anti-atoms were also jiggling from their own faint warmth, bouncing in every direction like popcorn. So a few would fly up no matter what gravity did. Scientists had to run the test again and again, over a dozen times, carefully adding up where the flashes appeared, hunting for a lean in the numbers, and the numbers leaned down. About 4 out of every 5 anti-atoms slipped out the bottom of the trap. Antimatter falls, just like a dropped stone, just like you. The mirror twin obeys the same gravity as everything else. Galileo's tower test, performed on the ghostliest substance ever made, gave the same answer he found with ordinary weights centuries ago. For most scientists, this was a relief. The great rule held, but it also quietly closed a door some had hoped would stay open. A few had dreamed that anti-gravity might explain one of the deepest mysteries in all of science. With that dream fading, the mystery only grew sharper and more urgent. Because if matter and antimatter behave the same, if the mirror is truly this perfect, then a terrifying question has no answer at all. Why does the universe contain any matter whatsoever? By all rights, everything should have destroyed itself long ago, leaving nothing behind but empty light. Here is a fact that should stop you cold. According to the best rules scientists have, you should not exist. The stars should not exist. The earth beneath you should not exist. The universe, by rights, should be a dark and empty place, filled with nothing but light and silence. Yet here you are, listening, made of solid matter. That single fact is one of the deepest mysteries in all of science. To see the problem, rewind to the very beginning, the first tiny fraction of a second after the birth of the universe. Everything was pure energy, blazing hot beyond imagining. As that energy cooled, it began to freeze into particles, exactly the way energy turns into matter inside CERN today. But there was a rule. Energy does not make matter alone. It always makes matter and antimatter together, in equal pairs, one twin and one mirror twin, every single time. So the newborn universe should have been perfectly balanced. For every particle of matter, one particle of antimatter, a perfect draw. And you already know what happens when a twin meets its mirror. They touch, and both vanish in a flash of pure energy. Total destruction. Follow that logic to its end, and it is chilling. If matter and antimatter were truly made in equal amounts, they would have found each other and annihilated every last pair. In the first moments of time, the universe would have wiped itself out before a single star could form. All that would remain today is a faint glow of leftover light spreading through empty space. No galaxies, no planets, no you. But that catastrophe did not happen. Somehow, matter survived. The proof is everywhere you look, in your hands, in the ground, in the sun overhead. Ordinary matter is all around, and antimatter is almost nowhere to be found in nature. The mirror twin has all but disappeared from the universe. Something saved us, and no one is completely sure what. Scientists have a clue, and it is astonishing in its smallness. In the early universe, the balance between matter and antimatter appears to have been off by the tiniest sliver. For every 1 billion particles of antimatter, there were about 1,000,000,001 particles of matter. Just one extra out of a billion. Picture a colossal battle at the dawn of time. 1 billion soldiers of matter face 1 billion soldiers of antimatter. They charge, they clash, and they wipe each other out, pair by pair, in a storm of light. When the dust settles, the battlefield is nearly empty, but not quite. Because of that one extra soldier per billion, a thin line of survivors is left standing. Every one of those survivors became the matter of the universe. Sit with the scale of that. Everything you have ever seen or touched, every star in every galaxy, is built from the leftovers, the 1 in a billion that did not get destroyed. We are the survivors of a war so lopsided it should have ended in nothing, which leaves the sharpest question of all. What tipped the balance? What broke the perfect mirror, just enough to let that one extra survivor slip through and build a whole universe? The answer hides in a tiny flaw in the laws of nature, a rule that quietly favors matter over its twin. Somewhere in the laws of nature, there is a flaw. A tiny, secret imperfection that treats matter and antimatter just slightly differently. That flaw is the reason a universe exists instead of nothing, and hunting it down is one of the greatest chases in science. For a long time, scientists believed the mirror between matter and antimatter was flawless. Every rule that worked for ordinary particles should work exactly the same for their twins, with nothing to tell them apart. A perfect reflection, with no cracks. If that were true, the great battle at the dawn of time would have ended in a perfect tie, and the universe would be empty. So the survival of matter told scientists something must be broken in the mirror. Then, decades ago, they caught the mirror lying. Deep in careful experiments, scientists watched certain rare particles decay, fall apart into smaller pieces, and they compared how the matter versions behaved against the antimatter versions. The two should have been identical. They were not. The matter and antimatter twins decayed in ever so slightly different ways. The mirror had a crack in it after all. Scientists gave this crack a name, but the name matters less than the idea. Nature does not treat matter and its twin as perfectly equal. There is a faint tilt, a slight favoring, hidden in the rules that govern how certain particles fall apart. It is small, easy to miss, and it took brilliant work to even prove it was real. But it is there. Finding that crack won the highest prizes in science, because it pointed straight at the answer. Here, at last, was a rule that could tip the balance in the early universe, that could leave one extra survivor per billion, that could explain why anything is here at all. It felt like the key to the greatest mystery of existence. Then came the crushing letdown. When scientists measured how big the crack actually is, they found it is far too small. The known flaw in the mirror can only account for a tiny fraction of the matter we see. Feed the numbers into the story of the early universe, and you still end up with a cosmos that should be nearly empty. The one extra survivor per billion needs a much bigger crack than the one scientists have found. Think of it like this. You come home to find your huge front door blown wide open, but the only wind you can measure is a soft breeze. The breeze is real, but it is nowhere near strong enough to have done the job. Something far more powerful passed through, and it left no other trace you can find. That is exactly where physics stands. The known crack is the breeze. The universe is the blown open door. So there must be a bigger flaw in the mirror, a stronger source of imbalance, still hidden somewhere in the laws of nature. Finding it would explain our very existence. And scientists believe the best place to catch the mirror lying again is inside a special kind of particle, born in the collisions at CERN. It is a heavy, short-lived speck that scientists nicknamed for its beauty, and the way it falls apart may be breaking the rules right in front of us. There is a particle so heavy and so fragile that it lives for barely more than a trillionth of a second before it shatters. In that impossibly short life, it may be showing scientists the crack in the mirror they have been hunting for decades. They named it, oddly enough, for beauty. Start with the pieces. The stuff you are made of is built from tiny building blocks called quarks. There are several kinds, and most everyday matter uses only the two lightest ones. But nature allows heavier, rarer kinds too, and one of the heaviest is nicknamed the beauty quark. It is a hefty cousin of the ordinary quarks, and it does not last. The moment it is born in a collision, a clock starts ticking toward its destruction. When the beauty quark falls apart, it can decay in many different ways, breaking into different sets of lighter pieces. And here is the key. The rulebook makes very precise predictions about how often each kind of breakup should happen. It says this path should be common, that path should be rare, and one particular path should be extremely rare, almost forbidden. Scientists can calculate the exact odds down to a fine point. That precision is a gift, because it turns the beauty quark into a trap for new physics. If some unknown particle or hidden force is lurking out there, it could nudge the beauty quark, changing how often it decays down each path. The rulebook predicts one set of odds. If the real world gives different odds, something the rulebook does not know about must be reaching in and meddling. CERN built an entire detector devoted to watching these beauty quarks fall apart, catching billions of them over the years. One especially interesting breakup involves a beauty quark transforming into a lighter cousin called a strange quark, while spraying out a matched pair of tiny particles in the process. The rulebook says this exact breakup should be very rare, and it predicts precisely how the flying pieces should behave as they scatter away. Think of it like a weighted coin with known odds. The rulebook swears this coin lands heads a certain fraction of the time, and it can tell you that fraction to many decimal places. Flip it a few times, and you learn nothing. But flip it billions of times, count every result, and even a tiny cheat in the coin will show up in the numbers. That is what watching billions of beauty quarks lets scientists do. They can catch a cheat far too small to see in any single flip. So, they flipped the coin billions of times. They watched beauty quark after beauty quark transform into a strange quark, carefully measuring the angles and rates of the pieces flying out, comparing the real results against what the rulebook demanded. For years, the numbers hovered in a strange place, close to the prediction, but leaning off in a way that made scientists uneasy. A hint, a whisper. Not quite enough to shout about. They needed more data, more flips of the coin, to know if the lean was real or just luck. And in the final month of the year 2025, a fresh batch of results arrived. When scientists opened it up and looked, the coin had landed the wrong way, more clearly than ever before. In December of 2025, a group of scientists finished checking a mountain of data, and what they saw made the whole field lean forward. A rare breakup of the beauty quark, watched billions of times over, was coming out wrong. The real world and the rulebook no longer agreed, and the odds that it was all just luck were shrinking fast. Here is what they measured. Scientists had watched the beauty quark transform into a strange quark over and over, tracking the exact angles at which the leftover pieces flew away. The rule book made a sharp prediction about those angles, but the real pieces kept coming out slightly off from the prediction, tilted in a way the rules did not call for. It was as if a hidden hand were reaching into the breakup and giving it a gentle push. To be sure it was real, scientists did the math on luck. Random chance can always fool you. Flip enough coins and you will sometimes get a strange streak that means nothing. So they calculated the odds that this mismatch was just a fluke, a run of bad luck dressed up to look important. The answer came out to roughly 1 in 16,000. In other words, if the rule book were perfectly correct, you would expect to see a mismatch this strong only about once in 16,000 tries. 1 in 16,000 is small enough to make your heart race. It is far less likely than tossing a coin and getting heads more than a dozen times in a row. Something odd is clearly going on with the beauty quark, and pure bad luck is looking like a weak explanation. Then came the part that made it even more exciting. A completely separate team, using a different detector at CERN, had studied a similar breakup on their own. If the first result were just a glitch in one machine, the second team should have seen nothing unusual. Instead, their numbers leaned the same way. 2 different experiments, run by different people, pointing in the same direction. That is exactly the kind of agreement that makes scientists sit up. If the mismatch is real, it could mean a brand new particle or a brand new force is out there, unknown to the rulebook, secretly nudging the beauty quark as it falls apart. That would be a crack in the 50-year-old rules big enough to see through, a first glimpse of physics beyond everything we know. It might even connect to the deepest questions, like the missing crack in the mirror or the invisible mass hiding in the universe. Picture a detective who has chased a suspect for years, catching only blurry glimpses. Now, at last, 2 different cameras have caught the same shadowy figure in the same alley, on the same night. It is not a clear photo of the face yet, but it is the strongest sign so far that someone real has been there all along. Excitement rippled through the field. Some scientists began to wonder aloud if this was the beginning of the biggest breakthrough since the Higgs. Yet the most careful voices urged everyone to slow down, because in physics, 1 in 16,000, as thrilling as it sounds, is still not good enough to declare that the rulebook is broken. The bar for rewriting reality is far, far higher. Imagine being almost certain you have made the greatest discovery in 50 years and still having to say the words, it might just be luck. That is the strange, brutal discipline at the heart of real science. Before anyone is allowed to rewrite reality, they have to clear a bar so high it has crushed many exciting results before. The beauty quark mismatch came with odds of roughly 1 in 16,000 of being a fluke. That sounds like a sure thing. In everyday life, if something had only a 1 in 16,000 chance of being an accident, you would bet your house on it. But particle scientists live by a far harsher rule because they have been fooled before, again and again. Here is their standard. To claim a real discovery, scientists demand that the odds of a fluke drop to about 1 in 3.5 million, not 1 in 16,000, 1 in 3.5 million. Only when a signal is that strong are they willing to stand up and say the rulebook is broken. Anything less, and they use a careful, cautious word. They call it evidence or a hint, never a discovery. Why be so strict? Because they run so many experiments and check so many numbers that rare flukes are bound to show up now and then. Flip enough coins, in enough labs, for enough years, and somewhere a coin will land heads 12 times in a row by pure chance. If scientists shouted discovery every time they saw 1 in 16,000, they would announce fake breakthroughs constantly, and the field would drown in false alarms. And this has happened. The history of physics is littered with thrilling anomalies that looked like cracks in the rulebook, only to melt away when more data came in. A tempting bump in the numbers appears. Headlines explode, hopes soar, and then, with more collisions, the bump shrinks back into nothing but a statistical ghost. Scientists have learned this lesson the hard way, over and over. Think of it like a winning streak at a slot machine. Get lucky a few times in a row and you might swear the machine is rigged in your favor. But you know that if enough people play long enough, someone is going to hit that streak by pure chance. The only way to know if a machine is truly rigged is to play it far, far more and watch the pattern hold. That is exactly what scientists must now do with the beauty quark. Collect more collisions, see if the mismatch grows stronger or fades away. So the beauty quark sits in a thrilling, agonizing middle ground, strong enough to be one of the best hints of new physics in years. Two separate detectors agreeing only makes it more tantalizing. Yet still short of the mountaintop, still one bad break away from being just another ghost that fooled everyone. The coming years will decide it, as more data pours in, and the odds either climb toward that towering bar or collapse back to nothing. If it holds, it would join a short and haunting list of clues that the rulebook is missing something huge. And one of the most famous clues of all came from a different particle entirely, a heavy, ghostly speck that spent 20 years wobbling in a way that seemed to whisper of a hidden universe. For 20 years, one tiny particle kept doing something it was not supposed to do, and every time scientists measured it, the same impossible answer came back. It wobbled just a little too much. That extra wobble looked, for 2 decades, like a doorway into a hidden universe. Meet the muon. It is a strange cousin of the tiny particle that whirls around inside every atom, the one that carries electricity through your phone. The muon is almost an exact copy of it, with the same charge and the same behavior, except for one thing. The muon is heavy, about 200 times heavier than its little cousin. It is like the same character, bulked up into a heavy weight. Muons do not last. Left on their own, a muon survives for only about 2 millionths of a second before it falls apart into lighter pieces. That is a blink beyond a blink. Yet muons are all around you, right now. They pour down from the sky constantly, born when rays from deep space slam into the top of our air. Hold out your hand, and several of these ghostly heavyweights are passing through it every second, sailing clean through your body without you ever feeling a thing. Because the muon is so heavy, it makes an unusually sensitive spy. Here is why. A muon acts like a tiny spinning magnet. Place it in a strong magnetic field, and it does not just sit still. It wobbles, slowly turning like a spinning top that leans and traces circles as it slows. Scientists can measure the exact speed of that wobble with breathtaking precision. Now, for the D part. That wobble is not set by the muon alone. The empty space around the muon is not truly empty. It froths with ghostly particles that flicker in and out of existence too fast to ever catch directly, appearing and vanishing in less than an instant. As the muon wobbles, every one of those flickering ghosts gives it a tiny tug, nudging the wobble faster or slower by a hair. This is what makes the muon so powerful. Its wobble carries the fingerprints of every kind of particle in the universe, even ones we have never seen. If there are unknown particles out there, hidden from every other experiment, they would still flicker in the space around the muon and leave their mark on its wobble. Measure the wobble precisely enough, compare it to what the known particles predict, and any gap would be a signature of something new. So scientists measured it with almost unbelievable care. They built a giant ring, sent muons racing around it, and clocked their wobble to a precision like measuring the distance across a country and being off by less than the width of a hair. Then they compared the real wobble to the number the rulebook predicted using only the known particles. The two did not match. The muon wobbled a touch more than the known particles could explain, and that tiny extra wobble refused to go away. Measurement after measurement, year after year, it hinted that unknown ghosts, particles beyond the rulebook, were crowding the space around the muon and pushing on its spin. For 20 years, that gap stood as one of the most tantalizing clues in all of physics, a whisper that a hidden world was waiting just out of sight. Then a fresh result arrived to settle it once and for all, and the answer shocked almost everyone. Before anyone could shout that the muon had cracked the rulebook, they had to answer a quieter, scarier question. What if the muon was fine and the mistake was in the math? Remember how the wobble works. Ghostly particles flicker in and out of the empty space around the muon, and each one gives its spin a tiny push. To predict the wobble exactly, scientists have to add up the push from every kind of particle that can appear. For most, this is hard but doable. For one group, it is a nightmare. That troublesome group involves the strong force, the glue that binds quarks. The particles it makes do not flicker politely, one at a time. They swarm, tangle, and pull on each other in a storm too messy for pencil and paper. Getting their contribution right is like predicting the exact shape of every ripple in a churning river. And this one messy piece was the largest source of doubt in the whole prediction. For years, scientists had two completely different ways to tackle it, and this is where the drama exploded. The first method leaned on real experiments, using measurements from other collisions to estimate the swarm's push on the muon. The second skipped experiments entirely. It used some of the most powerful supercomputers on Earth to simulate the swarm from scratch, crunching the raw laws of nature into a number. The trouble was, the two methods disagreed. The experiment-based recipe left a clear gap between theory and the measured wobble, the tantalizing hint of new physics. The supercomputer recipe gave a different answer. Its number came out larger, drifting toward the measured wobble, shrinking the exciting gap toward nothing. So the field split in two. One camp saw a doorway to a hidden universe. The other warned the doorway might be a mirage, born from using the wrong recipe for one messy patch of math. Both camps were brilliant. Both had strong arguments, and they could not both be right. Think of two expert chefs guessing the weight of a cake without a scale. One weighs every ingredient by hand. The other calculates it purely from a recipe on paper. If they disagree, the cake has not changed. One method is off. The muon's true wobble was the cake. The question was whose recipe to trust. As the supercomputer simulations got better, something uncomfortable happened. Their answer grew more trustworthy, and it kept pointing the same way, toward a prediction that matched the measurement. Slowly, the giant gap that had thrilled physicists for 20 years began to look less like a crack in the rulebook and more like a disagreement over arithmetic. The stage was set for a final showdown. On one side, the the most precise measurement of the wobble ever attempted. On the other, a freshly sharpened prediction from the world's theorists. When the two were finally laid side by side, the 20-year mystery would either shatter the rulebook or quietly dissolve. The answer came in the year 2025, and it was almost the opposite of what everyone had hoped. In the summer of 2025, the scientists behind the muon experiment released their final answer, the one they had spent years perfecting. It was the most precise measurement of the muon's wobble ever made, so exact that its uncertainty shrank to about 1 part in 8 million, a number that clean should have ended all argument. And it did, just in a way few people expected. The final measurement agreed almost perfectly with the earlier ones. The muon really does wobble at that exact rate. There was no mistake in the experiment. But when scientists placed it beside the freshly updated prediction, sharpened by years of supercomputer work, the two numbers nearly matched. The giant gap that had haunted physics for 20 years had all but vanished. Let that land. For 2 decades, the extra wobble looked like the strongest hint anywhere that unknown particles were hiding in the universe. Careers were built on it, dozens of new theories were dreamed up to explain it, and in the end, most of that gap seems to have come from using a shakier recipe for one messy piece of math. Sharpen the recipe, and the mystery melts. For many scientists, this stung. They had hoped the muon would be the crack that finally broke the 50-year-old rulebook. Instead, the rulebook stood firmer than ever. The heavy, ghostly muon, spinning like a top for 20 years, had been obeying the rules all along. Here is the part outsiders often miss. This letdown is actually science working exactly as it should. A real scientist does not chase a discovery at any cost. They chase the truth, even when the truth is boring, even when it crushes the result they were praying for. Being proven wrong, cleanly and honestly, is a kind of victory. Picture a detective who spends 20 years certain a suspect is guilty, then follows the evidence and clears the suspect's name. That detective did not lose. They served justice. Scientists tested their own rule book as hard as they possibly could, and it survived. That is knowledge, hard-won and honest. And the story is not fully closed. Even now, theorists are ironing out small disagreements in their recipes, tightening the prediction further. There is still a sliver of room, a faint chance, a tiny gap could return as the math gets sharper. Physics rarely slams a door completely. It leaves it barely ajar. Still, the lesson of the muon hangs over every exciting hint in the field, including the beauty quark result, waiting in the wings. A thrilling anomaly is not a discovery, it is a dare. It challenges scientists to measure harder, calculate better, and find out whether they are staring at a new universe or a smudge on the lens. Over and over, the famous anomalies have crumbled under that pressure. The rulebook keeps winning the headline fights. Yet here is the strange twist. While defending its old rules, CERN keeps stumbling onto things nobody predicted at all. Whole new creatures living inside the rulebook, particles so strange that for decades scientists were sure they could not even exist. For 50 years, there was a simple rule about how the building blocks of matter are allowed to gather. Then CERN found a particle that broke the pattern so cleanly that scientists had to admit the rulebook of matter had a chapter nobody had ever read. Go back to the quarks, the tiny blocks that build the heavy particles inside every atom. In nature, quarks are never found alone. They are always locked into groups, glued by the strongest force there is. And for decades, scientists saw them gather in only 2 ways. Sometimes 3 quarks bind together, which is how the protons and neutrons inside you are made. Sometimes a quark pairs with an antiquark, its own mirror twin, forming a lighter, flightier particle. 2 quarks or 3. That was the menu. Every particle made of quarks that anyone had ever found fit one of those 2 patterns. It became a quiet law of nature, so reliable that most people stopped questioning it. But the math never actually forbade other combinations. Back when quarks were first dreamed up, one of their inventors wondered aloud whether stranger clusters might exist. Could you glue 4 quarks together? Or even 5? On paper, nothing said no. Yet decade after decade, no one found a single one. They were like mythical animals, allowed by the rules but never seen in the wild. Then came the beauty quark hunters at CERN, sifting through billions of collisions. In the debris, they spotted something that fit neither pattern. When they carefully rebuilt what they were seeing, the answer was staggering. It was a single particle made of 5 quarks bound together at once. They called it a pentaquark, from the word for 5. Think of discovering a brand new shape of snowflake after a lifetime of believing snowflakes came in only 2. The water was always the same. The rules were always the same. But nature had been quietly building a third form all along, and it took a machine this powerful to catch one. The discovery was not a fluke. Once scientists knew what to look for, they found more of these 5 quark particles, different types with different combinations inside. A whole hidden family stepped out of the shadows, each a cluster the textbooks had never drawn. What makes this so important is what it reveals about the glue. The force that binds quarks is the strongest in nature, and also the least understood. It is so powerful and so tangled that scientists still cannot fully predict what it will and will not build. Every new kind of cluster is a fresh clue about how that mighty glue really works, filling in a map that is still mostly blank. And here is the humbling truth. These 5 quark particles were not rare accidents at the edge of possibility. They were there the whole time, in cosmic collisions across the universe, in the hearts of violent stars, waiting for someone to build a machine sharp enough to see them. We had simply never looked closely enough. 5 quarks was a shock, but it was only the beginning of the strangeness, because tucked in the same data was an even odder creature, one that would live far longer than it had any right to. Buried in the same flood of collisions was a particle that should have fallen apart almost instantly, yet it clung to existence far longer than anything like it. Its stubborn refusal to die told scientists that matter can hold together in ways they never expected. This one was built from 4 quarks glued into a single clump, so scientists called it a tetraquark, from the word for 4. Like the 5 quark particles, it broke free of the old 2 patterns, the simple pairs and trios that had ruled the textbooks. Once scientists knew these exotic clumps were real, they started finding more. A growing parade of 4 quark and 5 quark oddities pouring out of the data. Physicists began calling this collection the particle zoo because it filled with stranger and stranger creatures. Some clumps seemed to pack their quarks tightly into one ball. Others looked more like 2 smaller particles orbiting each other, loosely bound like a tiny pair of dancers spinning close. Nobody had a complete map of how these things were assembled, and each discovery redrew the picture. One tetraquark stood out. Most heavy, exotic particles die the instant they form, in a flash too fast to picture. But this particular 4 quark clump lasted much longer than its cousins, hanging on for a stretch that, in the particle world, felt like an age. That extra lifespan made it one of the most exciting exotic particles ever found, giving scientists a rare, longer look at how such a strange object holds itself together. Why does this matter? Because it all comes back to the glue. This force is a beast, and it behaves in a way opposite to your instincts. Pull 2 quarks apart, and instead of weakening with distance, like the pull between magnets, the force grows stronger, snapping them back like a stretched rubber band. Yank hard enough, and the band stores so much energy that it creates whole new particles rather than letting a lone quark escape. No quark ever travels by itself. That bizarre behavior makes the strong force fiendishly hard to predict. Scientists can write down the rules, but solving them for anything complicated is beyond even supercomputers. So every new clump the collider finds is a real-world test of a force we can barely calculate. Nature is showing its work, one strange particle at a time. Picture a master builder who knows only 2 shapes of brick house. Then someone shows them a tower, a bridge, a spiral staircase, all built from the same bricks. The builder realizes the bricks were always capable of far more than they imagined. That is what these exotic particles do to physicists. They prove the humble quark can assemble into architectures no one had drawn. Slowly, discovery by discovery, scientists are mapping the full range of what matter can be. Not only the ordinary trios inside your atoms, but a wild frontier of clusters that appear only when you smash things hard enough to set the glue loose. But there is a way to push the glue even harder. Instead of making new clumps of quarks, scientists found a way to tear matter apart completely, melting it into a substance that last existed at the dawn of time itself. There is a way to destroy matter so completely that it stops being matter at all, not by breaking it into smaller pieces, but by melting it into a glowing soup that has not existed anywhere in the universe for nearly 14 billion years. And CERN can make it on demand. To pull this off, scientists change their ammunition. Instead of firing lone protons, they load the machine with the nuclei of lead atoms, dense bundles packed with hundreds of protons and neutrons. Then they hurl these heavy bundles into each other at nearly the speed of light. The crash is so violent that the protons and neutrons themselves cannot survive it. Here is why that is such a big deal. Normally, quarks are locked inside protons and neutrons forever, chained by the strong force, never allowed to roam free. You cannot pry a single quark loose, no matter how hard you pull. But in the heart of a lead-on-lead collision, the temperature and pressure spike so high that the chains snap. The protons and neutrons melt, and for the tiniest flicker of time, the quarks and the glue that binds them break loose and flow freely, mixed together in a churning soup. Scientists call this soup the quark-gluon plasma. It is a state of matter unlike anything in your world. It is matter dissolved into its most basic ingredients, quarks and glue swimming free, the way they did in the first instance of creation. And that is the breathtaking part. This soup last filled the universe about a millionth of a second after the Big Bang, when everything was too hot for atoms, or even protons, to hold together. For that brief moment, all of reality was this seething plasma. Then it cooled. The quarks locked into protons and neutrons, and the ordinary universe began. When CERN makes this plasma, it recreates the newborn cosmos in miniature, opening a window onto the first tick of time. Scientists expected the soup to behave like a gas, thin and wispy, its freed quarks bouncing around loosely. Nature gave them a shock. The plasma flows like a liquid, and an almost perfect one, smoother than anticipated, with barely any internal friction. That single surprise rewrote what scientists thought the early universe was like. Think of ice melting into water, then go one impossible step further. Heat the water so violently that the water molecules themselves come apart, leaving a pool of pure, free, floating ingredients that no longer remember being water at all. That deeper melting is the quark-gluon plasma. It is matter undone, reduced to the state it wore at the very beginning. By studying how this soup flows, ripples, and cools, scientists learn how the infant universe behaved in its first heartbeat, and how the ordinary matter of today first froze out of the chaos. Every collision is a tiny replay of creation, but making a soup this exotic demands conditions almost too extreme to believe. To melt matter into free quarks, the collision has to reach a temperature so staggering it dwarfs anything else humans have ever produced, and even dwarfs the blazing core of the sun itself. Deep inside CERN, in the flash of a single collision, scientists routinely create the hottest thing in the known universe. Hotter than the surface of any star, hotter than the heart of any sun. For a sliver of a second, one tiny spot under the French and Swiss countryside becomes the most extreme furnace anywhere that we know of. When those lead nuclei smash together and melt into quark soup, the temperature at the point of impact climbs to a number hard to even say out loud. It reaches trillions of degrees. To give that meaning, compare it to the hottest place you can picture, the core of the sun. Down in the sun's center, where the pressure crushes atoms together and lights the star, The temperature sits around 15 million degrees, blistering beyond imagining. Now here is the jaw-dropper. The quark soup at CERN is more than 100,000 times hotter than that. The core of the Sun, the thing that warms our entire planet from 93 million miles away, would feel almost cool next to the fireball made in these collisions. Nothing else built by human hands comes close. Remember the strange fact from earlier in this journey. The magnets that steer the beams are chilled to near the coldest temperature possible, colder than deep space. And the collision points those magnets guide the beams into flash hotter than 100,000 suns. The coldest and the hottest places in the galaxy, sitting a short walk apart inside the same machine. Of course, this furnace is unimaginably tiny and unimaginably brief. The blazing spot is smaller than a single atom, and it exists for a flicker so short that light could barely cross a speck of dust before it cools and fades. There is no danger of it melting anything around it. There is simply too little of it, for far too short a time. It is a spark of primordial fire, gone almost before it is born. Why chase such insane heat? Because that temperature is a doorway to the past. The early universe was that hot, everywhere, all at once, in its first instant. The only way to study how matter behaves under those conditions is to recreate the heat, however briefly, and watch. CERN is building a tiny, fleeting Big Bang, over and over, just to glimpse the rules that govern the birth of everything. Picture striking a match in a pitch-black cave sealed for billions of years. The flame is small, and it dies fast. But in its brief light, for one moment, you glimpse walls no one has seen since the beginning. Each collision is that match, and the ancient walls are the laws of the newborn cosmos. From these tiny infernos, scientists have learned how the first matter flowed, how it cooled, and how the ordinary stuff of stars and planets first took shape. Each fireball is a message from the dawn of time. Yet the moment word spread that scientists were building conditions like the Big Bang, something unexpected happened above ground. Fear. Real, widespread, front-page fear. Some people became convinced that this machine, in its hunger to remake the beginning, might accidentally bring about the end of everything. In the months before the great machine first switched on, a strange panic swept the world. Lawsuits were filed. Frightened messages poured in. Some people were genuinely convinced that when scientists flipped the switch, the collider would create a black hole that would swallow the Earth whole. The fear ran so hot that a few researchers received threats. Where did this dread come from? It grew from a real, if wild, scientific idea. Black holes, as most people know them, are the crushed corpses of giant stars, regions where gravity is so fierce that nothing, not even light, can escape. They form when something enormous collapses. So the thought of a machine making one sounded absurd at first. But some theories whispered a stranger possibility. If the universe held hidden ingredients we had not yet discovered, gravity might behave very differently at incredibly small scales. Under certain exotic ideas, a collision violent enough might, just possibly, squeeze energy into a space so tiny that it pinched off into a microscopic black hole, not a giant star-eater, but a speck smaller than a single particle. The public heard black hole and pictured doom. They imagined a hungry pit appearing under Switzerland, growing and growing, devouring the lab, then the country, then the planet, until nothing was left. It was a terrifying image, and it spread like wildfire. Newspapers ran breathless headlines. Ordinary people lost sleep. A machine built to answer the deepest questions about reality had become, in the public mind, a possible doomsday device. To be fair to the warriors, the underlying question was legitimate. Any time humans build something that pushes into brand new territory, into energies never before created on Earth, it is only responsible to ask, could this hurt us? Scientists take that question seriously. They did not laugh it off. They studied it, carefully and openly, because the stakes were the entire planet. Picture the reaction if someone announced they were about to light the largest fire in human history in a crowded city. People would demand to know if it could spread. That is roughly how the world reacted to the idea of a machine reaching toward the conditions of the Big Bang. The instinct to ask whether it was safe was human. So, scientists faced two versions of one heavy question. First, could the collider actually make a tiny black hole at all? And second, far more important, if it somehow did, would that speck be dangerous or utterly harmless? The honest answer to the first was that it was extremely unlikely, possible only if some unproven ideas about hidden dimensions turned out to be true. In all the years the machine has run, no such black hole has ever appeared. The doomsday pit never opened. But the second question is where the real reassurance lives, and it rests on one of the most beautiful ideas in all of physics. Because even if the collider did make a microscopic black hole, that black hole would not grow, and it would not eat anything. It would do the opposite. It would vanish almost the instant it was born, thanks to a discovery that turned everything people thought they knew about black holes upside down. The great fear rested on one belief: that a black hole, once made, only grows, that it eats and never stops. That belief is wrong, and the reason it is wrong is one of the most surprising discoveries in the history of science. Black holes do not only swallow, they also leak, and the tiniest ones leak so fast they destroy themselves. For a long time, everyone assumed a black hole was a perfect trap. Anything that fell in was gone forever. Then, a brilliant physicist, working out the math where gravity meets the world of the very small, found something astonishing. At the very edge of a black hole, in the froth of empty space, particles can slip out. A black hole slowly bleeds away its own mass, glowing faintly into the darkness. Over time, it shrinks. Here is the twist that saves the planet. The smaller a black hole is, the faster it bleeds. A giant one, made from a dead star, leaks so slowly it would take longer than the age of the universe to fade. But a microscopic one, the kind people feared, would be so small that it would leak at a furious rate. It would evaporate almost the moment it appeared. We are not talking about years, or seconds, or even a blink. A tiny black hole made in a collision would erase itself in a stretch of time so short it makes a flash of lightning look eternal. It would pop into existence and vanish before it could travel the width of an atom, long before it could swallow a single particle, let alone a planet. The doomsday pit would be gone before anyone could notice it was there. Think of a drop of water flicked onto a surface hotter than a stove. It does not sit there and spread. It sizzles away to nothing in an instant. A microscopic black hole is that drop. The smaller and hotter it is, the faster it disappears. There is no time for it to become a threat. So the terrifying image, the growing pit devouring the earth, gets the science exactly backward. A tiny black hole would be the most fragile, short-lived thing imaginable. A spark that snuffs itself out faster than any spark you have ever seen. And there is one more layer of comfort, so powerful it settles the matter. It comes from looking up at the sky. Space is full of natural particles called cosmic rays, tiny bullets flung out by exploding stars and other violent events. Some carry far more energy than anything the collider can produce, and they have been slamming into the Earth's atmosphere for billions of years. If those natural collisions, more powerful than anything at CERN, could make a world-eating black hole, the Earth would have been destroyed long ago. So would the moon, the sun, and every star in the sky, all bombarded constantly. Yet here they all are, still shining. Nature has been running this experiment at higher energies across the universe since before the Earth even formed, and nothing has ever been swallowed. But black holes were not the only nightmare people imagined. Another doomsday idea was stranger still, a kind of matter that could, in theory, turn everything it touched into more of itself. There was another doomsday idea, and to some, it sounded even scarier than a black hole. A hypothetical speck of matter so strange that, If it existed, it might reach out and turn ordinary matter into copies of itself, spreading like a rust that never stops. Scientists gave this imagined speck a fittingly odd name, a strangelet. To understand the fear, go back to the quarks. Ordinary matter is built mostly from the two lightest kinds, but there are heavier kinds too, including one nicknamed the strange quark. A strangelet, if it were real, would be a clump holding a heavy dose of these strange quarks all bound together, forming a new and unfamiliar kind of matter. Here was the nightmare. What if this strange matter were more stable than ordinary matter? What if, when a strangelet touched a normal atom, it converted that atom into strange matter too, releasing energy and growing larger? Then that bigger clump could touch more atoms, converting them, growing again. In the worst imaginings, a single strangelet could chew through the entire planet, turning the Earth into a lifeless ball of strange matter in a runaway chain reaction. It made for a horrifying picture, and when scientists began smashing heavy nuclei together, some feared these collisions were the perfect recipe for cooking up such a seed. The same dread that surrounded black holes wrapped itself around this idea too. But when scientists studied it, the fear fell apart on several fronts. First, most physicists concluded that strange matter, if it exists at all, is almost certainly less stable than ordinary matter, not more. An unstable strangelet would fall apart on its own in a flash, unable to convert anything. Rather than a spreading rust, it would be a puff of smoke. Second, the conditions inside the collider work against it. Strangelets, if they could form, would prefer cold, calm surroundings. The collisions at CERN are the opposite, a blaze hotter than 100,000 suns. Trying to grow a delicate strangelet in that inferno is like trying to grow a snowflake inside a furnace. And then there is the final, unbeatable argument, the same one that quiets every doomsday fear about this machine. The universe has already run the experiment, countless times, for billions of years. Natural collisions far more violent than anything at CERN happened constantly across the cosmos, on the moon, on distant stars, in the hearts of exploding suns. If those collisions could brew a world-ending strangelet, the damage would have shown up long ago, somewhere in the sky. It never has. The moon, ancient and battered, is still the moon. The strongest proof of all is quieter than any calculation. The machine has now run for well over a decade, making these exact heavy collisions again and again, millions upon millions of times. No black hole has appeared. No strangelet has formed. No pit has opened. The Earth spins on, exactly as it always has. The doomsday predictions, every one, have been answered by the simplest evidence there is. We are all still here. With the fears laid to rest, scientists could return to the real reason they built this machine. Not to end the world, but to find what most of it is actually made of. Because the ordinary matter in you, in stars, in everything you can see, adds up to only a small slice of the universe. The rest is missing, invisible, and utterly unknown. Look up at the night sky. Every star, every galaxy, every glowing cloud of gas adds up to only a small fraction of what is really out there. The overwhelming majority of the universe is invisible. Scientists cannot see it, cannot touch it, and after decades of searching, still do not know what it is. They simply call it dark matter. The first clue came from watching galaxies spin. A galaxy is a vast whirlpool of stars, turning slowly in space. Using the known laws of gravity, scientists calculated how fast the outer stars should move, based on all the visible matter they could count. Then they measured the real speed. The outer stars were racing far too fast. Spinning that quickly, they should be flung out into space, scattering the galaxy apart like mud off a spinning wheel. Yet the galaxies hold together. Something is gripping those speeding stars, some source of gravity far greater than everything we can see. There must be a huge amount of extra mass, invisible and silent, wrapped around every galaxy like a hidden scaffold. That unseen mass is the dark matter, and there is a stunning amount of it, For every pound of ordinary matter in the universe, there are roughly 5 pounds of this invisible stuff. Sit with that. Everything humans have ever seen, every atom we have ever studied, is the minority. The universe is mostly built from something we have never held. Dark matter does not shine, does not block light, and slips through ordinary matter like a ghost through a wall. It is passing through your body this instant, and you feel nothing. So how do you catch a ghost? This is where CERN enters the hunt. If dark matter is made of some unknown particle, then maybe a violent enough collision could create a speck of it right here on Earth. The trouble is, dark matter would slip through the detectors unseen, just as it slips through everything else. You could make it and never see it leave. Scientists came up with a clever trap. They rely on one ironclad rule. In any collision, the total energy and motion has to balance out, like a ledger that must always add up. So, after each crash, they carefully total the energy and motion flying out in the visible debris. If some is missing, if the ledger does not balance, then something invisible must have carried it away. That missing slice would be the fingerprint of a dark matter particle, escaping unseen but leaving a hole in the accounts. Think of weighing a sealed box before and after, and finding it lighter, even though you saw nothing leave. You would know, for certain, that something slipped out through a crack you could not see. Missing energy is that lighter box. It is how you detect the invisible by the shape of the hole it leaves behind. For years, scientists have combed through countless collisions, hunting for that telltale imbalance. And so far, the ledger has stubbornly balanced. No clear sign of a dark matter particle has appeared. The most abundant stuff in the universe stays just out of reach, refusing to show its face. Some scientists think the reason we cannot find it is that we are missing a piece of the puzzle even bigger than a single particle. Perhaps the answer hides in something far stranger, in dimensions of space we cannot see. You live in a world of 3 directions: left and right, forward and back, up and down. Every place you have ever been fits inside those 3. It feels complete, obvious, the whole of space. But what if it is only part of the story? What if there are more directions, hidden all around you, too small to notice? This is one of the boldest ideas in modern physics. Some theories suggest space has more than 3 dimensions, with extra ones curled up so impossibly tiny that we can never see or feel them. Imagine every point in the air around you secretly containing more directions, wound up smaller than an atom, smaller than a speck inside a speck. You would walk through them constantly and never know. It sounds like pure fantasy. So why would any serious scientist believe it? Because hidden dimensions might solve one of the deepest puzzles in all of physics, the puzzle of gravity, and why it is so absurdly weak. You might not think of gravity as weak. It holds you to the ground after all. But consider this. A tiny magnet, small enough to hold in your fingers, can pick up a paperclip, lifting it against the gravity of the entire planet. One small magnet beats the pull of the whole Earth. Compared to the other forces of nature, gravity is bafflingly feeble, and no one knows why. Extra dimensions offer a wild answer. What if gravity is actually as strong as the other forces, but most of its power leaks away into those hidden directions, spreading out where we cannot follow? By the time it reaches our 3-dimensional world, only a faint trickle is left. The gravity you feel would be the weak leftover of a mighty force draining into unseen space. Picture a bright lamp in a room with hidden doors leading to other rooms. Most of the light pours out through those doors, and only a dim glow reaches you. You would swear the lamp was weak, when really its light is escaping somewhere you cannot see. In this picture, gravity is the light, and the hidden rooms are the extra dimensions. If this idea were true, CERN might find proof. In a powerful enough collision, a particle might get knocked sideways into one of these hidden directions, disappearing from our world entirely. To the detectors, it would look like energy simply vanishing, slipping out of our 3 dimensions into somewhere we cannot follow. It would leave the same kind of hole in the ledger that dark matter might. a clue written in absence. So scientists searched. They combed through collision after collision, looking for particles that seem to leap out of our reality, and for other strange signals hidden dimensions might leave behind. If the extra directions were there, and close enough to reach, the machine had a real chance of catching them. The result, so far, is silence. No particle has been caught vanishing into another dimension. No clear trace of hidden directions has appeared. If they exist at all, they are even smaller or stranger than the simplest theories hoped, still buried beyond the machine's reach. This search is tangled up with another beautiful idea, perhaps the most beloved theory in all of physics. An elegant vision that would tidy up the rulebook, explain the dark matter, and answer a dozen mysteries at once. There is only one problem. Despite decades of searching, the collider cannot find a single trace of it. There is a theory so elegant that many of the world's smartest physicists were sure it had to be true. It would solve mystery after mystery in a single stroke. It would explain the invisible dark matter, tidy up the messy math of the rulebook, and reveal a hidden order beneath everything. For decades, scientists chased it with total confidence, and the collider has broken their hearts. The theory is called supersymmetry, and its core idea is gorgeous in its simplicity. It says that every known particle in the universe has a secret partner, a heavier twin we have never seen. For every ordinary building block, there would be a hidden, weightier version waiting to be discovered. The whole family of particles we know would suddenly double, revealing a mirror set of heavyweight cousins. Why would nature bother with all these extra twins? Because they would fix things that are badly broken in the current rulebook. The math of the standard model has some ugly, awkward corners. Numbers that seem impossibly fine-tuned, as if the universe balanced a pencil perfectly on its tip by luck. The hidden twins would quietly cancel out those problems, steadying the math and making it click into place. To a physicist, that kind of elegance feels like a sign of truth. Even better, one of those hidden twins might be the dark matter itself. The lightest undiscovered partner could be stable, invisible, and abundant, exactly the kind of ghostly particle needed to explain the unseen mass gripping every galaxy. In one beautiful move, supersymmetry could solve two of the biggest puzzles in science at once. It was almost too perfect to resist. When scientists switched on the great machine, many fully expected these heavy twins to come pouring out of the collisions. The energies looked right. The theory looked right. Discovery seemed just around the corner. Some researchers built entire careers on the belief that they would soon meet these hidden partners face to face. Think of a treasure map so detailed, so convincing, that everyone was certain the gold was buried right where the X marked the spot. All that remained was to dig. So they dug through years of collisions, sifting the debris for any sign of the heavy twins. The treasure was not there. Collision after collision, year after year, the hidden partners refused to appear. Scientists searched the energies where the simplest versions of the theory promised they would be, and found nothing, empty ground where the gold was supposed to lie. Each search pushed the possible twins to be heavier and rarer, backing them into smaller and smaller corners. This is one of the great quiet dramas of modern science. A theory can be beautiful, elegant, and beloved, and nature can still simply say no. The universe is under no obligation to match our sense of what is graceful. Supersymmetry may still exist in some altered form, hiding at energies beyond the machine's reach. But the simple, gorgeous version that inspired a generation has been pushed to the brink. Yet even as the machine kept failing to find the twins scientists wanted, it succeeded in catching a completely different kind of particle. One no collider had ever trapped this way before. A true ghost, one that pours through your body by the trillion, almost never touching a thing. Right now, as you listen, trillions of ghostly particles are passing straight through your body every second. They slip through your skin, your bones, the chair, the floor, the entire planet, as if none of it were there. You feel nothing. You will never feel them. They are called neutrinos, and they are the most elusive particles ever studied. Neutrinos are almost nothing. They carry no electric charge, they weigh almost zero, and they barely interact with anything at all. Most matter, to a neutrino, is empty space. A neutrino could fly through a wall of solid metal light years thick and have a decent chance of coming out the other side untouched. They are the closest thing to a true ghost that physics has ever found. They are also everywhere. The sun pours out unimaginable floods of them every moment, and they wash over the earth day and night, streaming through the ground beneath your feet, even at midnight, having passed clean through the whole planet to reach you. Exploding stars fling them across the galaxy. They are among the most common particles in the entire universe, and yet, because they touch so little, they are maddeningly hard to catch. For decades, scientists studied neutrinos from the sun, from the sky, and from nuclear reactors. But there was one obvious source no one had ever managed to catch them from directly: a particle collider. Every violent crash at CERN should spray out neutrinos by the swarm, born in the chaos. The trouble was, being ghosts, they would sail right through the giant detectors without leaving a mark, lost among all the other debris. So scientists built a special trap and placed it far down the tunnel, off to the side, right in the path where these collision-born neutrinos would fly. Then they waited, hoping to catch the faint, rare moment when one of the ghosts actually bumped into something and left a trace. And it worked. For the first time, scientists directly caught neutrinos made in the crashes of a collider, a genuine first, a brand new window opening after decades of the ghosts slipping past unnoticed. Collisions had been making these particles all along. Now, at last, someone had caught them in the act. Why does catching a ghost matter so much? Because neutrinos are messengers from the strangest corners of physics. They come in different types, and bizarrely, they can shift from one type to another as they travel, changing identity in mid-flight like a shapeshifter. That behavior is deeply tied to some of the unsolved mysteries of the rulebook. Studying the high-energy neutrinos born in collisions gives scientists a fresh way to probe those secrets, in a range they had never been able to explore. Picture spending your whole life knowing a phantom drifts through your house, felt only in faint, rare chills, until one day you finally build a device that catches it on camera. Suddenly, the ghost is real, studyable, a source of answers instead of a rumor. That is what catching collider neutrinos did for physics. The rulebook keeps standing strong against the famous anomalies, yet the hints keep coming, small and stubborn. And one of the most puzzling of all came from measuring the weight of a single particle, a number that stubbornly came out heavier than the rules say it ever should. Sometimes the deepest crack in a rulebook is hidden inside a single number, a weight. Scientists set out to measure the mass of one particular particle, expecting the answer the rules had long predicted. Instead, one careful measurement came back too heavy, and it set off an argument that still has not been settled. The particle in question carries one of nature's fundamental forces, the force behind certain kinds of radioactive decay, the same force that helps power the sun. This particle is heavy, short-lived, and its exact mass is something the rulebook can predict with great precision. The rules do not leave much wiggle room. They say it should weigh a very specific amount, no more, no less. For years, measurements agreed with the prediction, and all was calm. Then a team that had spent a decade painstakingly analyzing old collision data announced a new, ultra-precise measurement of that mass. When they revealed their number, it landed like a thunderclap. The particle came out noticeably heavier than the rulebook allowed, not by a wild amount, but by far more than their careful measurement should have been off. If that heavier weight is correct, the consequences are enormous. This mass is woven into the very fabric of the rulebook. It is tied to the Higgs, to the other forces, to the whole delicate web of numbers that hold the theory together. Nudge that one weight, and the entire structure starts to groan. A heavier value would mean some unknown particle or force is subtly tugging on it, a hidden influence the rulebook does not account for. It would be a genuine crack. Naturally, the result electrified physics, and it demanded a second opinion. A number this important, this shocking, could not stand on one measurement alone. Other teams, including those at CERN, set out to weigh the same particle themselves, using their own collisions and their own methods to see if they too would find it running heavy. And here is where the story twists. When one of the major experiments at CERN finished its own careful measurement, the weight it found sat comfortably in line with the rulebook. No excess, no crack. Their particle weighed just what the rules predicted. So now there are conflicting answers on the table. One landmark measurement says too heavy. Another says perfectly normal. Both were done by careful, expert teams. Both cannot be fully right. Think of two trusted jewelers weighing the same gold coin on two different scales and getting different weights. The coin has one true mass. One of the scales, or the way it was read, must be off. Until they figure out which, no one can say whether the coin is ordinary or something special. That is exactly where physics stands with this particle's weight, caught between two respected results that flatly disagree. Sorting it out will take even more precise measurements, more collisions, and careful work to hunt down the cause of the mismatch. It joins the beauty quark hint on a short list of tantalizing puzzles, each a possible doorway, none yet proven. And that is the pattern of this whole frontier. Clue after clue, hint after hint, always just short of certainty. To finally push these mysteries over the line, scientists need something they do not yet have, far more collisions than the current machine can deliver, which is exactly why they are about to make it vastly more powerful. The greatest discoveries of this machine were hidden inside a tiny handful of collisions out of trillions. So there is an obvious way to find more secrets, make more collisions, many, many more. And that is exactly what scientists are about to do, in an upgrade so ambitious it will transform the machine into something far mightier than it is today. The current collider is already staggering, crashing bunches of protons together tens of millions of times a second. But the rarest, most interesting events, the ones that might reveal new physics, are so uncommon that even that blistering rate is not enough. To catch a whisper this faint, you need to listen far longer or shout far louder. Scientists chose to shout louder. The plan is to dramatically increase the number of collisions packed into every moment, squeezing the proton beams tighter and cramming more particles into each crossing. The goal is to boost the collision rate by around 10 times. 10 times more crashes means 10 times more chances for something rare and wonderful to appear in the debris. The scale of data this will produce is dizzying. In just a few years of running, the upgraded machine is expected to gather more collision data than the collider has produced in its entire history up to now. It is like going from sipping through a straw to opening a fire hose, a flood of information so vast that scientists are already redesigning their computers just to handle it. Why does more data change everything? Because it turns faint hints into firm answers. Remember the beauty quark, with its tantalizing 1 in 16,000 oddity, still short of the mountaintop standard for a true discovery. The way to push it over that line, or knock it down for good, is more collisions. Watch the beauty quark fall apart enough additional times, and the truth will surface. Either the strange behavior grows into an undeniable signal, or it fades like so many hints before it. More data is the judge that finally decides. The same is true for every open puzzle. The conflicting weight of that force-carrying particle, the hunt for dark matter's missing energy, the search for the heavy twins that supersymmetry promised. All of them are starved for data, waiting for more collisions to tip them from maybe into yes or no. The upgrade is the feast that could settle them. Picture a photographer trying to capture a shooting star. In a single night, they might catch nothing, but leave the camera running for many nights, gathering every faint streak, and the rare event will eventually appear, clear and undeniable. The upgrade lets scientists keep the shutter open far longer, catching the rarest streaks the universe has to offer. Getting there takes real sacrifice. The machine has to shut down for a long stretch and be rebuilt in major ways, its magnets and detectors upgraded to survive the intense new torrent of collisions. It is a massive, years-long effort, all in service of one goal: more crashes, more chances, more truth. Yet, even this enormous leap may not be the end of the road, because some of the deepest questions might need energies this machine can never reach, no matter how many collisions it makes. To truly finish the hunt, scientists are already dreaming of a successor so vast it would dwarf everything built so far. A machine to end all machines. Deep in the planning rooms of CERN, scientists are drawing up blueprints for a machine so enormous it makes today's mighty collider look small. A ring not 17 miles around, but closer to 56. A tunnel 4 times longer, buried under the same countryside, built to chase the last great secrets of reality. They call it the Future Circular Collider. The reasoning is simple, even if the machine is not. To create heavier, rarer particles, you need more energy in your collisions. To reach more energy, you need to accelerate your particles over a longer distance before they crash. A bigger ring gives the protons more room to build up speed and power, letting scientists smash them together far harder than ever before. Bigger tunnel, bigger energy, bigger reach into the unknown. With that reach, the new machine could go hunting for the answers that have slipped through our fingers for so long. It could search for dark matter directly, at energies the current collider cannot touch. It could probe the Higgs with extraordinary precision, studying the field that gives everything mass in far greater detail. It could look for the hidden twins of supersymmetry, the extra dimensions, and whatever unknown force might be nudging the beauty quark. A fresh chance at every mystery, with a sharper tool than humanity has ever built. The dream comes with a heavy price, and it sparks real debate. A machine this vast would cost tens of billions of dollars and take decades to build, stretching across a good part of this century. Some scientists argue the money and effort could achieve more if spread across many smaller projects, or that there is no guarantee the giant machine will find anything new at all. Others answer that the biggest questions in existence are worth the boldest tools, and that humanity has always pushed forward by daring to build what seemed impossible. It is a genuine argument, with thoughtful people on both sides, and it is far from settled. Whatever gets built next, step back and consider what this machine has already shown us. Buried under 2 countries, it recreates the fire of the newborn universe, makes the rarest substance in existence, and catches ghosts that pour through us unseen. It found the particle that gives the world its weight. It melted matter into the soup of creation. It weathered every doomsday fear and proved them empty. And it keeps testing the deepest rules we have, again and again, refusing to let us grow comfortable. Here is the thought to carry with you. Everything we know, the entire rulebook that describes all of reality, is almost certainly incomplete. There are missing pages, and we feel their absence in the invisible mass of the cosmos, in the strange survival of matter, in the faint puzzles that will not fully die. The universe is still keeping secrets, and it guards the biggest ones fiercely. But we are getting closer. Every collision, every strange particle, every stubborn anomaly is a step toward understanding what reality is truly made of and why it exists at all. Somewhere in the debris of these crashes, or in the machine that comes next, may lie an answer that changes everything we believe about the world and about ourselves. The rules we trust are being pushed to their limits, and the moment they finally break, the moment reality reveals what has been hiding underneath, will be one of the greatest turning points in the story of our species. We are the generation that gets to watch it happen.